Okay, so let's look now at page 2 of the notes for section 3.3. So we're dealing with finding the zeros of polynomials. And so we have here a polynomial function. And to start with, we look and we say, well, we would look for factors of 18 divided by factors of 6. So that seems like a lot, but if you notice one thing about this function is that we could divide through this function by 6, right? Because, what we really want to sort of do is, even though it's a function, we want to sort of think of it as, an equation. And so we could factor out or divide through, in this case, by 6. And so if we do that, then the function or equation, if you want to think of it more of an equation, becomes 2x cubed plus 11x squared minus 7x minus 6 equals 0. Okay? And so now we have fewer things to worry about, right? Like I know 18 can't be a 0 and 9 wouldn't be a 0 because now I have to look at factors of 6 divided by factors of 2, okay? So let's set that up. And this is that new process of using synthetic division. It's sort of a faster shortcut method. All right, and so we put just the coefficients, of course, so we do 2. And let's double check. Degree 3 means we should have 4 terms, 1, 2, 3, 4, so we don't have any missing terms. All right, next is an 11, -7, and -6. And then remember we put the remainder line sort of between those last two numbers. All right, let's try 1. All right, so we bring down the 2. We multiply 1 times 2, and we add it to the 11, so that's 13. We multiply 1 times 13, that's 13. Add it to -7, so that is 6. We multiply 1 times 6 is 6. We add it to -6, and that is 0. All right, so we got lucky on this first one, and we found one of our zeros. So that means x equals 1 is one of our zeros. Now, think about this. How many zeros do we have? We have 3, right? We found 1. The resulting, this 2, 13, and 6 are the coefficients then of our depressed polynomial. So our depressed polynomial is 2x squared plus 13x plus 6 equals 0. And so we need to find two more zeros. We don't use, once we get down to a degree 2 depressed polynomial, we stop, right? Because we know how to solve quadratics. We don't have to keep looking using synthetic division. Generally, it's going to be faster to either factor or use quadratic formula. So let's see if this factors. It's generally worth the extra second to check. If not, then we'll go and we will use the quadratic formula. So let's just take a second and see if it works. So we have 2x and x, and then 6. So I can't use, well, I could use 6 and 1. I guess that's possible. And with this 13, that's kind of what I think I'm going to want, right? So I want this 2 times the 6. That gives me 12. And then 1 more will give me 13. So that seems like it works. So this is a plus. So that means they're both the same. They both have to be positive. So plus and plus. All right, and so then we set each one of those equals to 0. So we get x is equal to -1/2, and x is equal to -6. All right, so we have our 3 solutions. We have x equals 1, x equals -1/2, and x equals 6. All right, now, some of you might be wondering, like, wait a minute, up here we divide it through by 6. That changes the equation. Did we also just change the solution? So are the solutions different now? So I'm going to open up Desmos and show you, graph some of these, and we can see what the solutions are visually, and see if does it matter when we graph the original versus when we graph this reduced. And then I've got a bunch of different graphs I'm going to show you as well. Okay, so this Desmos is kind of following example number 4 in our notes. So let's I'm going to turn on a couple of the graphs here. So that was the original function that we had, and then we divided it through by 3, I think. Yeah, and then we got this one. And so you could see that regardless of whether or not I divide it through by 3 or not, they have the same solutions. They pivot through those same points. So that one was, where was it? It was like at 1, 0, and the other one was at -1/2, and the last one was at -6, right? So those are our 3 solutions, and they're the 3 solutions regardless of whether we multiplied through or divided through. So what I did is I took equation, I guess the original equation, and then I said, well, what if we put something out in front of it like a, and we multiplied through by a, and then this little function allows me to change the value of a. So you can see how it doesn't matter what we multiply or divide through by, it will have the same zeros. So it's like the zeros are sort of the hinge things, that the hinge points that the function fluctuates about. And so even if I made it negative, you see it flips back around the other way, and it's still the same solutions, even if I multiply through by a negative. It flips it about the x-axis, shrinks it and stretches it in the vertical direction, but we get the same zeros either way. All right. All right, so let's go on to part B of example 4. This one, they're sort of nice. They tell us that there are no integer zeros. So it's all the factors of 2 divided by all the factors of 6. So that would be plus or minus 1 plus or minus 2 taken one at a time divided by all the factors of 6. So that's plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. So you can see there's a lot of possibilities here. Okay, but as a hint, I'm telling you that there are no integers, so don't try, 1 over 1 or 2 over 1. 2 over 2 won't work. Those would all be integers. Okay, so you've got to try some fractions in this case. Okay, so let's try some. So I'm going to set this up. Now think about this too. We have a degree 4. That means we're looking for 4 zeros, 4 solutions. How many do we need to find using this method of synthetic division? We have to keep going until we get a depressed polynomial of degree 2. That, like we saw over here, once we get a depressed polynomial of the degree 2, we then can either solve that by factoring or by quadratic formula. All right, we don't want to keep going. So we have a polynomial of degree 4. Once we find our first zero, our depressed polynomial will be degree 3. We look for another one, and once we get that second one, then we'll have a depressed polynomial of degree 2. So we need to find 2 zeros using synthetic division. Okay, so x, let's put it in here. So we have 6, -1, we have 4, we have -1, and we have -2. Okay, and we put a little vertical line there. All right, so I'm going to try 1/2 to start with. And so I'm going to bring down the 6. I'm going to multiply 6 by 1/2. That is 3. Add it to -1, so that's 2. Multiply by 1/2, that's 1. add to 4, that's 5. And now look what's happening. When I multiply by 1/2 by 5, that's 5 halves, minus plus a -1. So that would be 3 halves. But you can see very quickly, this is not going to be a 0, right? We're multiplying by 1/2. It's going to be 3/4. It just gets worse and worse, right? So once you kind of start getting fractions in here, probably pretty safe to assume that we're not going to get a remainder of 0. Okay, so let's try -1/2. All right, so that was no good. If you want to put a light line through it, we're not using these numbers. We're going back to the original numbers again. Okay, don't obliterate it in case you want to go back and check your work again. All right, so I'm going to bring down this original 6. It's like that line doesn't exist almost, right? So you want to sort of think about covering that up. All right, so we bring down this 6. -1/2 times 6, that's -3. And we add that to -1, so that's -4. Okay, then we multiply these together. That's +2. I add that to the 4, and I get 6. I multiply, that's -3. I add that to -1, I get -4. And now it looks like it's going to work, doesn't it? So -1/2 times -4, that's 2. Add it to -2, and that's a 0. All right, so we found our first 0. Okay. Now we should try. So now we don't use these numbers anymore. Now we work with the depressed polynomial. So we put another line, and now the remainder line goes there. Okay. Now technically, we should try -1/2 again. Remember that we can have duplicated zeros, right? Non-distinct zeros, okay, with multiplicities of 2. So I'm going to bring down this 6. Again, I'm not using these anymore. I'm now using the depressed polynomial. If I kept going and dividing these every time, then I would have to find all 4 of the zeros using this method. I would not be able to chip away. So now I have a depressed polynomial of degree 3. I do it again, and I get a depressed polynomial of degree 2, at which point I stop. All right, so let's check if -1/2 has a multiplicity of 2. I bring down the 6. I multiply. That is -3. Add it to -4. That's -7. And I can already see, okay, that's going to start giving me fractions, and that's just not going to work. So we can forget about that one. And let's try 2/3. Okay, so again, we're going to ignore these numbers. It's these up here that we're going to use. So bring down the 6. All right, so 1/3 of 6 is 2, times 2 is 4. Add it to -4, that's a 0. All right, so now we multiply 2/3 times 0, and that's 0. Add it to 6, and that's 6. We multiply 6 by 2/3 again. 1/3 of 6 is 2, times 2 is 4, and you can see adding 4 to -4, that gives us 0. Okay, so we found our next or second 0. Now, we just got lucky. Sometimes think about how many different things you would have to check. I got lucky. Okay, so now we have this depressed polynomial. So that depressed polynomial is 6x squared plus 6 equals 0, right? The center term is missing, the linear term. So we can just solve this. Let's take the 6 to the other side, and then let's divide by 6. So I get x squared is equal to -1. Then we're going to take the square root of both sides. We have x is equal to plus or minus the square root of -1. Well, that's just equal to plus or minus I. All right, so that is our last 2 solutions. So we had, for part B, we had -1/2, +2/3, and plus or minus I. So you can see why it's really important that we stop after we have a depressed polynomial of degree 2, because indeed we would have never found these two solutions, plus I and negative I, by using synthetic division. Synthetic division would only give us rational answers, not complex. Okay, so it's really important that you kind of chip away. You have, starting with the degree 4, the depressed polynomial next will be degree 3, then degree 2, at which time we stop and we use some method, either factoring. In this case, we just solved it by doing some algebra. Okay. All right, let's go on to the next thing. Oh, I was already talking about multiplicities up here, and this will make more sense when I talk about multiplicities of 2. It just means that it's a repeated root, basically, a repeated solution. All right, polynomial function of degree n has at most n distinct zeros. So that is the number of zeros theorem. It essentially means that the number of degrees tells us the number of solutions, or number of zeros. So there's 3 terms: 0 of the function, solutions or roots. All 3 of those are synonymous terms. All right. So you might hear me say, what are the roots of it? What are the solutions to it? What are the zeros of it? Okay. We will generally say that the polynomial function of degree n has n zeros. However, they just may not be distinct. They might be repeated. So for example, if we look at number 5, 4x squared minus 20x plus 25 is a second degree polynomial, and so it should have 2 zeros. But when we factor it, you see that it's it's a perfect square trinomial, right? So it's 2 binomials, or really we write it as 1 binomial squared. So we know that this gives us what? One of the solutions, if we set that equal to 0, is x equals 5 halves. But they're both the same, right? Both binomials are the same. So as it turns out, it's not 2 distinct zeros. It's 1 zero that has a multiplicity of 2. And that's kind of what I was saying up here, is that we don't know until we check this if negative 1/2 was a repeated root, or repeated 0, or a solution with multiplicity of 2. Indeed, it wasn't, because it did not have a 0 there. So it was not a double root. All right, so let's try number 6. 6 says, find the polynomial function of degree 3 with real coefficients that satisfies the following conditions. And so this is the condition we're looking at. So if a 0 is negative 3, what binomial would we have solved? So that is just x plus 3, right, would be the binomial. And so for negative 2, it would be x plus 2. And for 5, it would be x minus 5. Now, if we FOIL all that together, that is a degree 3 polynomial that has these solutions, but it may not fit these conditions. And so in order to make sure it fits that conditions, kind of like what we saw in the Desmos demo, we would need to stretch or shrink this function so that it would hit a particular point. So if we think about it, negative 1, 6. So we want at negative 1, we want it to be up at 6. So we need the point, the curve, to go through that point as well, negative 1, 6. And the only way we'll be able to do that is if we have some sort of coefficient out in front that will shrink and stretch the function, kind of like what we saw in Desmos. Okay, and so that is our function. Okay. And so what we want to do is just FOIL all this out. So we'll get a, and this will be x squared plus 5x plus 6, x minus 5, still there. Okay. And now we want to FOIL all this stuff together. And so that will be a, and it'll be what? X cubed minus 5x squared plus 5x squared minus 25x plus 6x minus 30. Okay, and then if we FOILed all that, you pause this video and just try all that on your own and see if you get this. But we would simplify that. X cubed, what do we have? X cubed minus 19x, the 5x squares, negative 5x squared and 5x squared, those are opposites, so they'll cancel, and then minus 30. Okay, now we know when we put a negative 1 in for x, this whole thing should be equal to 6. So let's think about what that would be. So if we have 6 is equal to a times, and we put in a negative 1, so that's negative 1 cubed minus 19 times negative 1 minus 30. Okay? And so all that's going to be 6 is equal to a, and that'll be negative 1 plus 19 minus 30. And all that is 6 is equal to a times negative 12. So that gives us an a value of negative 1/2. So we could, I don't have room to write it, but we could essentially then, let's just put it right up here. So we could have negative 1/2 and f of x. So we could write that as our solution. Maybe better yet, you might want to distribute this negative 1/2 into that. All right, let's make sure we can see that that's negative. Negative 1/2. Okay, so that would be sort of the solution. Okay, same kind of thing here. So it says 4 is a 0 of multiplicity 3. So I could list it 4, 4, and 4, or I could just say it has a multiplicity of 4. So that means the binomial will be x minus 4, but it'll be cubed. Okay, that's what our function is. And again, they told us that when we go past, so if we have the point here at 2, we're way down here at negative 24. So the point would be way down here. Okay, so and again, in order to get our graph to go through that exact point, we need a coefficient out in front of this thing. All right, now we'll learn later on this year how to expand a binomial cubed using something called the binomial theorem. But for now, just you'll have to FOIL it out if you want to pause the video and try foiling all this out and then seeing if you get the right answer. But I'm just going to go ahead here. So this is x cubed minus 12x squared plus 48x minus 64. All right, so again, I know how to expand a binomial to the third power using the binomial theorem. You'll learn that soon enough. All right, so let's plug in what we know. We know the function is going to be equal to 24 when we put in a 2, right? So let's put a 2 in for these things. That's going to be an 8. Put a 2 into this. That's going to be negative 48. Put a 2 in for x here, and that's going to be plus 96. And then the last part is 64. Okay? So that's negative 24 equals a. If we simplify all that, we get negative 8. Okay? Then if we divide through by negative 8, we know that a has got to equal 3. So let's rewrite it. We have f of x is equal to 3 times, and then we can say x cubed minus 12x squared plus 48x minus 64. And that's fine unless we say like fully simplified, right? It probably wouldn't be a bad idea to also, it would be simpler to evaluate it sometimes, maybe if we have with this too. X minus 4 quantity cubed would not also be a bad, So if they say fully expand it, then probably you want to distribute this 3 into this. But either one of those would probably be an acceptable answer, depending on sort of how the question is being asked. Okay? All right, this last part on this page is the conjugate zero theorem. So if f of x is a polynomial function with real coefficients And one of the zeros is a plus bi. So that means one of the zeros is complex. So we have a complex zero, a plus bi. Then we also know the conjugate, a minus bi, must also be a zero. They always occur in pairs. So we want the polynomial of least degree. So they give us two solutions here. Be careful, this is not 3 and negative I. It's negative 4, and then the other solution they gave us is 3 minus I. So that also means that I know that one solution has to be 3 plus I. Complex zeros, complex solutions always occur in pairs. So if you have one, you can't just have one. You'd have to have its conjugate as well. All right, so let's write the binomials that we have here. So the function is going to be x, what, from this negative 4, it's going to be x plus 4. And then we want to write x minus the 0, right? So x minus negative 4 or x plus 4. For complex ones, do x minus and then put the 0 in. 3 minus I. And then the other one is x minus 3 plus I. So I would do this so that you're distributing the negatives properly there. All right, let's rewrite that. So we have x plus 4, and then we have x minus 3 plus I. We distribute that negative to the 3 and to the negative I, so it's plus I. And then x minus 3 minus I. So you notice the signs change between these two, between the 3 and the I, not between the x and the 3. So it's x minus 3, x minus 3. It's the plus I and minus I that are different. Okay. So now we want to expand this out. And so what I would suggest doing is leaving this alone for now and expand this out. Now, this first time that I do this, I'm going to show that this is looks like a trinomial and acts like a trinomial. So we have a trinomial times a trinomial. So that means I'm going to have 9 terms. Now I'm going to write them all out this first time, but know that in the future I'm not going to, because there's too many things that just cancel. And so if you're aware of this, you don't have to write it all out. Just write out the things that don't cancel. But to start with, I'm going to write them all. All right, so we do x times, hang on, let me turn on a light. Maybe that will help. I'm a little bit in the shadow down here. Okay, so so now we're going to, I'm going to hold my hand here by the x. So x times x, x squared. X times negative 3, negative 3x. X times negative I, negative, and then it's just up to you if you want to put the x first or the I first. I'm going to do it as negative xi, but just be consistent so you know what things are going to cancel. Okay, then I go on to the negative 3. Negative 3 times x, negative 3x. Negative 3 times negative 3, positive 9. Negative 3 times negative I, that's positive 3i. Now I go on to the I times x, positive xi. Again, I'm putting the x first so that way I can see that this and this are really the same thing. If I switch them around, it's harder to see that. All right, then I have what? I times negative 3, negative 3i. And then I times negative I, negative I squared. Now notice that this ix and the ix, those are going to cancel. Also, the 3i and the negative 3i. So anything with just an I in it, I don't bother writing down because I know it's going to cancel, and it always will in this situation. Okay, so what's left is really x plus 4. Let's simplify this. It's really x squared minus 6x, and then I have a plus 9, and the I squared is negative 1, so negative I squared is positive 1 plus 10. Okay, and so then my last thing I got to do is FOIL all this out, multiply this binomial by the trinomial. All right, and I've already done that, so I'm going to write it out pretty quickly here just for the sake of this video. So pause this video and then do it, and then see if you did it correctly. Okay. All right, so we get x cubed minus 6x squared plus 10x plus 4x squared minus 24x plus 40. And then combining like terms, of course, let's rewrite it again. F of x is equal to, and we can do combining like terms, we have x cubed minus 2x squared minus 14x plus 40. And then, you know, this didn't give us a point that it had to go through like we did up here. But if they give us this, then we would just want to sort of include like an a out in front, and then, you know, plug in the values for this one. But in this case, they didn't ask us to do that. So we don't need, you know, we don't need those parentheses at all either. Okay? All right, so that's page 2.